Determine whether the series is absolutely convergent or conditionally convergent. The series is so this is an alternating series. So first we check for absolute convergence. Which means, so let's write what is mod of an. So we have to check if this series whether it's convergent or divergent. So this series is same as to check for its convergence, we do what integral test. So let f of x then because when I substitute 0, I get ln1 which is 0. So this tends to infinity as t goes to infinity. So it means divergent. So this series is divergent, not this. So it means absolute convergent is not true. So now let's check for conditionally convergent. So we perform alternating series test because this is an alternating series. Alternating series test. AS is alternating series test. So if you recall, right, which is 0. So this first condition is true. Second, we see bn plus 1. So this is less than, right, because this denominator is larger than this. So bn plus 1 is less than bn. So means convergent. So it is conditionally convergent. So our answer then becomes this given series is conditionally convergent. So the answer is CC, conditionally convergent, CC. Let's do another problem. Here we have to use ratio test. Number 15. Use the ratio test to determine whether the series is convergent or divergent. So let's see. AN is and AN plus 1 . Now ratio test means we have to evaluate the quantity absolute value of AN plus 1 over AN. There is some cancellation. This pi n will cancel out this pi n, leaving behind a pi. Similarly, this will cancel out this, leaving behind a -3. So we have n plus 1 times pi -3. Because it's absolute value, and there's n here also. Because it's absolute value, so we can ignore this negative. So we are left with pi over 3, 1 plus 1 over n. Absolute value, negative goes away, pi over 3, n plus 1 over n. So you divide n over n, you get 1 and then 1. Next, we have to evaluate what is the limit n going to infinity which is this will go to 0 as n goes to infinity. This is pi over 3 and pi over 3 is greater than 1. So therefore, we conclude that the given series is divergent. So in ratio test, we compute the absolute value of an plus 1 over an. We can drop the minus because it's absolute value, take the limit, and if it's greater than 1, then it's divergent. Let's do next problem. Number 17. So an is and an plus 1 so note, if you don't know, n factorial is same as n times n minus 1 times n minus 2 times so then n plus 1 factorial will be n plus 1 times n minus 1. So this is same as 1 times n factorial. So this is something important to remember. Now let's write what is absolute value. So here n plus 1 factorial, I have written it like this. Why I have written like that? So that you can cancel out. Now this equals to Now there's n in denominator, and there are two cost functions of n. So before we can take the limit, we have to understand how these two functions or their ratio would behave. So let's see. So let me write some values here. So cos pi over 3 is half. Right? When n is 1, it's pi over 3. It's 2 pi over 3. It's minus half. Then when n is 2, 2 pi over 3, and 3 pi over 3, which is cos pi, negative 1. When n is 3, we get cos pi, 4 pi over 3, negative half. Then when n is 4, 4 pi over 3, 5 pi over 3. Is half. And then when n is 5, you get cos 2 pi, which is 1. So this ratio for all n's will always be the ratio of these quantities. And this can at most be, so if say n is 5, if n is 5, you get 2. So you get 1 divided by 1 over 2. So this implies this ratio of cos is less than 2 over n. So what it means is we can write equal to some c over n. The c goes to 2. It can be 2 or it can be 1/2. So if we have some other, if we have 1/2 in the numerator and 1 in the denominator, then you have 1/2. So c, which is something finite. So this means limit n tends to infinity, c over n is 0. Which is less than 1. So the given series is then absolutely convergent. Or AC. So let's do next problem, which is 29. So here we have to use root test. Let's look at the series. So the absolute value of an here is so whenever you see n or any power of n in the exponent, try root test. So let's compute what is the same as so then the limit now what is this limit? So this limit turns out to be e. Which is greater than 1. And how is this e? We've derived it before. So greater than 1 would mean divergent. So let's see how we compute this limit. So if you recall how to do it, so we let y as then we take ln of y, which gives us we take the limit of ln of y. But this is right now with infinity times 0 form. Because ln1 is 0. So we cannot apply L'Hopital rule. So we rewrite this as so we move this x downstairs. Because now you have when x goes to infinity, you have ln1 which is 0 and 1 over x which is 0. So this will be 0 over 0 form. So here we can apply L'Hopital. And that would give our answer. Not 0. So the limit of ln y will be 1. So for y, it will be e to the 1. And because it's greater than 1, so it's divergent. Let's do more problems. Number 31. So use any test to determine whether the series is absolutely convergent, conditionally convergent, or divergent. So this is an alternating series. But as always, we'll first check for absolute convergence. Just AC. So in order to check for absolute convergence, we're checking this series. Now, note ln x is less than x. Or we can call it n if you want. Where n is greater than equal to 2. For n or x greater than equal to 2, this is true. And ln n is less than n. So therefore 1 over ln n is greater than 1 over n. Now this is a p series. P equal 1. Which is divergent. So by comparison test, is divergent. So it means this is not absolutely convergent. So now next we check for conditionally convergent. Now check for conditionally convergent. So we use alternating series test. So AST is alternating series test. So if you recall, Bn is over ln n. Zero. So this condition is correct. Second, Bn plus 1 over ln n plus 1, which is less than so Bn plus 1 is less than Bn. So this is also true. And this is true because ln x is an increasing function. So 1 over ln x would be decreasing. And 1 over ln x would be decreasing. So which is why n plus ln of n plus 1 is less than ln of n. So this is convergent by alternating series test. But this convergent is conditionally convergent. So the answer is conditionally convergent. CC. Let's do another problem. $35. So now let's first write what is A. So n is an exponent. So we should try root test. So let's write what is so the limit is, so this form is infinity over infinity. So we can apply L'Hopital rule. So we get derivative of n is 1 over n. So the limit after applying L'Hopital rule is infinity. So divergent. So this series here is divergent. So this is all. Maybe for one problem I can give you a hint, but you can try doing it yourself. So the hint for problem 37 is tan inverse n is less than pi over 2. So now use comparison test. This is written comparison. Write it here. So now use comparison test. Okay.